Hello and welcome back everyone. Today we're going to continue talking about the star formation phases. If you take a look at frame A on the top, this is a region called M20, and it shows observational evidence for 3 of those phases in the birth of a star. The parent cloud, that big area represented there, is stage 1 of table 19.1, which we talked about in last lecture. The region labeled contracting fragment likely lies between stages 1 and 2. And the mission nebula itself, M20, results from the formation of 1 or more massive stars, stages 6 and 7. If you take a look at the picture in frame B on the bottom left, we get to see a close-up of the area near region B. And you can see that it's drawn in ovals. It's especially dense knots of dusty matter. And if you take a look at frame C, we see an infrared image of the same scene, and it's revealing cores thought to be stellar embryos. So the beginning of stellar formation. The Orion Nebula, M42, has many contracting cloud fragments, protostars, and newborn stars. If we take a closer look at the Orion Nebula, starting from frame A, we see the constellation Orion, and the region where the Orion Nebula is located at is the middle star of Orion's sword. If we enlarge that area and we take a look at frame B, we see how the nebula itself is partly surrounded by a vast molecular cloud. Various parts of this cloud are probably fragmenting and contracting, with even smaller sites forming protostars. Frame C is a false color radio image of some intensely emitting molecular sites. Frame D is a nearly real color visible image of embedded nebular knots, which are thought to harbor protostars. And frame E is a high-resolution image of one of many young stars surrounded by disks of gas and dust where planets might ultimately form. These are 2 protostars in the Orion Nebula at around stage 5 in their development. If you take a look at frame A, we see the edge-on infrared image of a planetary system-sized dusty disk in the Orion region, and you can see heat and light emerging from the center. On the basis of its temperature and luminosity, this unnamed source appears to be a low-mass protostar on the Hayashi track, so around stage 5, in the HR diagram. Looking at frame B, we see an optical face-on image of a slightly more advanced circumstellar disk surrounding an embedded protostar in the Orion Nebula. Protostars are believed to have very strong winds, which clear out an area around the star roughly the size of the solar system. Looking at frame A on the top, we see the nebular disk around a protostar, and in this case, it can be a site of intense heating and strong outflows, forming a bipolar jet perpendicular to the disk, as represented by the artist's depiction. In frame B, as the disk is blown away by the wind, the jets fan out, and eventually in frame C, they merge into a spherical wind. In contrast to this, take a look at frame D, which is an actual infrared image of a hot young star at right, whose powerful winds are ripping away the disk at left, surrounding a sun-like star at the center. This particular system is located about 750 parsecs away in the star-forming cloud IC 1396. These two jets are matter being expelled from around an unseen protostar, if you look in that little square on the bottom of the picture. This view of the Orion molecular cloud shows the outflow from a newborn star still surrounded by nebular gas. The inshot shows a pair of jets called HH1 and HH2 formed when matter falling into another protostar, still obscured by the dusty cloud fragment from which it formed, creates a pair of high-speed gas jets perpendicular to the flattened protostellar disk. The jets themselves are nearly 1 light-year across. Several more Herbig-Haro objects can be seen at the top right. Now, a Herbig-Haro object, HH, is a small nebula associated with star formation that varies irregularly in brightness. At the top right in the picture, you see a very oddly shaped one that kind of looks like a waterfall. That may be due to an earlier outflow from the same protostar responsible for HH1 and HH2. Which brings me to brown dwarfs. Brown dwarfs are very cool, low luminosity stars whose mass is not sufficient to ignite nuclear fusion. So a brown dwarf will never be on the main sequence on the HR diagram. And because it has such low luminosity, they're very difficult to observe directly because they're very dim. These two images right here are images of two binary star systems, each believed to contain a brown dwarf. Notice the difference in luminosity between the star and the brown dwarf. The brown dwarf is pointed towards by the arrow. So compare that little bright dot with that big, massive, luminous star. Now, how does the actual collapse of the interstellar cloud begin? What triggers it? Well, shock waves from nearby star formation can be the trigger needed to start the collapse process of an interstellar cloud. If you take a look at this picture right here, it shows you generations of star formation, starting from the top left. In frame A, we have star birth from the interstellar cloud. In frame B, we have shock waves that are expanding, and they're leading to frame C, more star bursts and more shock waves, which are going to lead to even more star bursts. So we have a continuous cycle of star formation in many areas of our galaxy. Just as in a chain reaction, all stars trigger the formation of new stars ever deeper into an interstellar cloud. Other possible triggers: death of a nearby sun-like star, a supernova, density waves in galactic spiral arms, or galaxy collisions. And these are all things we're going to talk about in subsequent chapters. This region represented here in this picture may very well be several generations of star formation. Let's talk a little bit about star clusters. Because a single interstellar cloud can produce many stars, and because they're going to be produced at the same time from the same interstellar cloud, then we know that they should have the same age and composition. So studying star clusters is an excellent way to figure out the effect of mass on stellar evolution. In this picture here, we have a newborn cluster called NGC 3603. And we also see a portion of the larger molecular cloud in which it formed. The cluster itself contains about 2,000 bright stars and lies some 6,000 parsecs from the Earth. The field of view shown here spans about 20 light years. Radiation from the cluster has cleared a cavity in the cloud several light years across. The inset frame shows the central area more clearly, including the most massive star in the region, called Sher 25, which is above and to the left of the cluster. It is already near the end of its lifetime, having ejected part of its outer layers and formed a ring of gas. Many low-mass stars, less massive than the Sun, can also be seen. This is a picture of a young star cluster called the Pleiades. The HR diagram of the stars is shown below. This star cluster is an example of an open cluster. So what is an open cluster? It's a grouping of stars of about 10 to 10,000 stars with an open, transparent appearance. And the stars are not tightly grouped, but they're close enough together. This is a picture of a globular cluster. Note the absence of massive main sequence stars on the HR diagram below. And you can also see that we have lots of stars in that cluster that are in the red giant region. A globular cluster is a star cluster containing several thousand to a million stars, and it has a spherical shape. So they're all bunched up very close together. They're gravitationally bound. The differences between the HR diagrams of the open and globular clusters are that the globular clusters are very old, whereas the open clusters are much younger. The absence of massive main sequence stars in the globular cluster is due to its extreme age. So those stars have already used up their fuel and have moved off the main sequence, and they're starting their slow process towards stellar death. The presence of massive, short-lived O and B stars can profoundly affect a star cluster. And that's because as they blow away dust and gas, they can do that before it has time to collapse. So this is a nice picture of a simulation of such a cluster. In the congested environment of a young cluster, star formation is a competitive and violent process. So large protostars may grow by quote-unquote stealing gas from smaller ones, and the extended disks surrounded most protostars can lead to collisions and even mergers. The cluster environment can play a crucial role in determining the types of stars that form. This frame from a supercomputer simulation shows a small star cluster emerging from an interstellar cloud that originally contained about 50 solar masses of material distributed over a volume of 1 light year across. Remnants of the cloud are shown here in red. This image shows such a star-forming region in the Orion Nebula. In frame A, we see a short exposure visible light image that shows the nebula itself and 4 bright O-type stars known as a trapezium. In frame B, a Spitzer Space Telescope view of the same part of the nebula shows more clearly the irregular gas and dust amidst many young stars still embedded in that dust. Which brings me to the last thing I would like to talk about today, the discovery of Eta Carinae. At the heart of the Carinae emission nebula, shown in the middle figure, lies a remarkable object called Eta Carinae. That's the object at the right bottom. It has an estimated mass of about 100 times the mass of the Sun and a luminosity of 5 million times the solar value. It is one of the most massive stars known. It probably formed only a few 100,000 years ago, and it had an explosive, though brief, life. In the mid-19th century, Eta Carinae produced an outburst that made it one of the brightest stars in the southern sky, even though it lies some 2,200 parsecs away from the Earth, which is a very long way compared to most of the bright stars visible in our night sky. During this great explosion, which peaked in 1843, the star expelled more than 2 solar masses of material in less than a decade and released as much visible energy as a supernova explosion. Yet, it somehow survived the event. So this is a very curious case, and your book goes into great detail on page 486. So, chapter 19 in a nutshell, stars begin to form when an interstellar cloud begins to contract. The cloud itself fragments as it contracts. Fragments continue to collapse and fragment until their density is high enough to prohibit any further fragmentation. The fragments heat up enough to radiate a significant amount of energy. At that point, we have the stage of a protostar. The protostar continues to collapse. When the core becomes dense and hot enough, fusion begins. The star continues to collapse until the inward force of gravity is balanced by the outward pressure from the core. The star is now in the main sequence, and we have the hydrostatic equilibrium. More massive stars follow the same process, but more quickly. Less massive stars form more slowly. Star formation has been observed near emission nebulae. And we know that the collapse of the interstellar clouds may be initiated by shock waves. One cloud itself will tend to fragment into many stars, not just a single star. And when that happens, we have the formation of a star cluster. Open clusters are relatively young, small, and randomly shaped groupings of stars. Globular clusters, on the other hand, are very old, very large, and spherical groupings of stars. Study chapter 19.4 through 19.6. Be able to explain the nature of interstellar shock waves and their role in star formation, and explain why stars form in clusters. Until next time.